Hello everyone. In this lecture I will talk about frames and machines, and we'll learn how to draw their free body diagram. So let's see what frames and machines are. So frames and machines consist of pin connected members. Okay, frames and machines are both pin connected members. Frames are usually used to support loads. Okay, that means they are usually stationary. Machines are used to transfer or transmit and alter the effect of force. Okay, first one is a stationary, second one usually has moving parts. So they're pin connected members. If you remember, truss was also pin connected members. Remember, slender pin connected members that they also use to support loads. So what is the difference between frames, machines, and trusses, and how to figure that out? So one thing that I want to mention is trusses, if you remember, they were slender pin connected members, forces only at the ends or only at pins, which made them a two-force members. So truss consists of two-force members only, versus frames and machines, forces could be anywhere. For both of them, which makes them a multi-force member. So they can have two-force members, but for sure they have multi-force members or three-force members too. So that just means more than two. Two-force members, remember, they were either in tension or they were in compression. For a member to be a two-force member, the forces needs to be opposite and equal and share the same line of action, which is the same axis of the thin members. That was trusses. In frames and machines, that is not the case anymore. You can have something like that, but you might have a force in the center as well. So the forces are not only applied at the pins, or you can have more than forces applied at trusses, or members of frames and machines. So the way that we handled frames and machines, trusses, let me write down here. So truss, the way we had two options. Option one was method of joints. So we drew FBD of a joint. Or method 2 was method of sections, which we made a cut and then draw FBD of section. Okay, method of joints, you have a joint, you have a force, and you figure it out. Okay, similar to equilibrium of a particle. Sigma Fx, sigma Fy, summation of moments. Method of sections, you cut the truss in half and then applied something like this and treat it as a rigid body, similar to a rigid body equilibrium. You had, sorry, totally made a mistake. You don't have sigma moment. Summation of Fx equals 0, summation of forces in y. Now you have summation of moment. Equilibrium of particle, you only have Fx and Fy. So that was the truss. 2 force members only. So now we have frames or machines. We treat them differently. So now this is multi-force members. We draw free body diagram of each individual member. So we take it apart and we draw free body diagram of individual members. Some of them are probably going to be a 2-force member, which has a simple free body diagram like this, or compression. But the other ones are going to be a multi-force members, 3-force member or more, and then their free body diagram is going to be different. So for frames and machine, we take it apart. For truss, we either draw free body diagram of the joint or the section. We do not take truss apart. So let's see. To do free body diagram of the frame or machine, step 1, we disassemble. Means take it apart. Okay. We have to isolate each member, meaning draw outline of it, and then you have to put all active forces, put all reactive forces. These are the 3 steps for drawing any free body diagram. Isolate, active forces, reactive forces. So that was the step 1 for free body diagram. But to further analyze it, we have to identify all 2-force members. And I will explain why, and why is that important, to figure out which members are 2-force members. The other thing that is important is that forces that are common to any 2 contacting members where there was a pin and now you're taking it apart, they act equal but opposite. That is also very important. Opposite sense or direction. So that is all I had. I can add another bullet point here as important, but this is kind of obvious, but it's good to mention it. If these 2 members that we took it apart, if you do not take them apart and treat them as a system, if two members are treated as a system, means you're treating them together. Or in other words, there are two members that you didn't take apart, which we're going to see in examples why that might be a case. Then that means the forces on those pins that you didn't take apart are internal forces. Kind of like, if you remember, when we had a truss, we made a cut, you revealed the forces, right? Only when you make the cut, you reveal the forces, the internal forces. So same thing, if you are not taking two members apart, then you are not revealing anything. But if you take them apart, then you are revealing forces that are opposite and equal with each other. So we're going to see this through examples, and I promise it's going to get more clear. So let's see. Draw a free body diagram for the following structure. State whether it is a frame or a machine or a truss. Okay, so let's look at this arrangement that we have. I mentioned truss has only two force members. Frames and machine, they can have more. So they can have multi-force members. Let's look at members. I see some members. I see AC and I see DB. Those are the two main members of this structure. And AC or DB, only forces that are present are at the end. So this is a two-force member. Versus AC, this is a multi-force member, because the forces are not only towards the end. So I see point B, something in the middle. I see ropes at the end. So that's multi-force member. It's a stationary, so I'm going to take it as a frame. So the way that we analyze this, take it apart. Okay. It depends on how many ways and how many different members you can take apart. I would like to just take those two members apart, AC and DB. I don't want to take the pulleys and all those ropes and all that apart. Okay. That's my DB. And this is my AC. Okay. Let's start with DB. DB is a two-force member. So eventually it is either in compression or is in tension. So whatever way I put forces on it, eventually the resultant force should be in the axis of this member. It's a two-force member. I have pin at point D, and we learn that pin can have an X and Y. So look what I do here. I put a DX here and a dy here. I know I put dx in negative direction, but because it's an unknown, I can put it anywhere I want. But look, the resultant force of these two is in this direction. So the other force at point B, so this is a case of, the way I drew it is a case of tension. So at point B, I'm going to draw it this way. Okay. Another way of drawing it, dy, dx, bx, by. Another way of drawing it, FB or FB, FD, it's a two force member, and I know that FD should equal FB. Or you can totally draw it in compression. Another way of drawing it. These are all different ways that you can draw free body diagram of DB. The important thing is, if you put a dx and dy, their resultant force should be in this direction, and they should be opposite way. So all of these are acceptable. The next thing, when you go to point to AC, look where these two members will attach to each other. And that's point B. So if you drew B pointing this way, you should put a point B or whatever. Let's call this BD and DB. So we know that they're similar. BD going opposite direction. Remember, for common forces common to any two contacting member forces common to any two contacting member act equal but opposite. Two contacting member, B and B. The forces on those two, it's a common force. When I put it back together, those should cancel each other out. The rest is kind of easy. So I have a pin at A, so that one also has an AX, AY. They're unknown. I can put it anywhere I want, or any direction, any sense I want. Point B, I see a tension in cable, tension. I see another tension. Remember, this is all one cable, all going around. Point C, I see a pin. There's a tension going down. I see another tension going the other way. Okay, this is my free body diagram. Some people like to draw it as like this, which is totally fine. T, T, BD, AX, AY, CX, CY. If you want, you can add another tension there too. Okay, there depends on how much you want to break down your problem. Okay, let's look at another one. This one looks like a truss, but it's not a truss because of two reasons. First of all, I don't see no triangle. Remember, a simple truss started with a triangle, so it had three members. Second of all, AB, that is a two force member, but BC is a three force member. So then this acts as a frame or a machine, maybe, if this can move. I don't think so, but it doesn't really matter which way we take it. Our analysis is going to be the same. So now that I know it's either a frame or machine, I'm going to disassemble and take it apart. Okay, let's just start with a two force member, which is this one. A two force member. I have a pin at A, so it has an AX or AB. I just like to put the resultant force there, force AB. Because I drew that one pointing up, I have to draw this one opposite direction, FAB. So this member, the way I drew it, is in compression, and it's a two force member. Some people might like to draw it as AX and AY. That is totally fine as long as the resultant lays on the axis of the member. Meaning this is wrong if you draw AX and AY. That is wrong because the resultant force is pointing this one and it's not in the axis of the member. So at point B, whatever you put makes it wrong and it's not a two-force member anymore. Okay? Point B is common between the two members, so the forces needs to be opposite and equal in magnitude. Point C, so before going to point C, I have a 2000 Newton pointing there. Remember, a three-force member, they should either be parallel or concurrent. This one, these can't be parallel. So the only option left is concurrent. Means whatever forces I put on point C, the resultant force should pass through that point as well. Point C is a pin, so it has a CX and CY. And if I draw my CX this way, CY this way, their resultant, well, not exactly going to that point, but so that means my point needed to be a little bit changed right there. Okay, there we go. So this is the free body diagram. Again, this was another option. So this is also correct. This is correct. This was wrong. Or if you put your CX and CY any other way, so let's say you put CX and CY like that. So the other force is kind of pointing the other way and not going to meet the other two forces. That doesn't make it concurrent, so that doesn't make it a three-force member. Let's look at this one. Well, it's not a truss for sure. It's a movable part for transferring load, so it's a machine. As soon as I know it's a machine, meaning I have to draw or disassemble its member. How much you want to disassemble it, it's totally up to you. Okay, I'm gonna have this member, this huge arm, kind of main arm, this one, and then I'm going to take another member. I'm assuming that this is connected somewhere back there, so IH, and it's going to be a this one, I think it's a two-force member, so whatever I put on there, I am going to do it this way. Point H is common, so it needs to have opposite and equal direction. Point F, let's assume that there's another two-force member. That's fine. The other way is whenever you see a pin, any time you see a pin on a member, just put an X and Y for it. So let me just put an FX and FY for it. I see point E attached to another two-force member, EB. Doesn't matter if I put it tension, compression. Let's put it in compression. EB, so this is FEB, FEB. Point E is common between the two, so the forces needs to be opposite and equal. When I put them together, they need to cancel each other out. Let's move down. I see point C attached to another two-force member, CB. Going this way, this one needs to be opposite and equal direction. Therefore, the other one is also opposite and equal direction. I see the bucket. I see point D. It's connected to a multi-force member. So what I do is I put a DX, DY, because I'm seeing a pin. I see a pin at point A. But for that one, I got to be careful because it's attached to member AB. So I can put an AX and AY, AY, AX. So that makes the other one going this way, member A, B, A, B, force AB, force AB. So let's see what happens. If the resultant force is this way, so if I put this point back here, these two forces will cancel each other out. So now you see why I put AX and AY going the other way in FAD that way. So this is a two force member, two force member, two force member, two force member. This is multi-force. I'm not done, by the way. Multi-force members. Let's go back to our color. Point D. So that one needs to be opposite. DX needs to go the other way. DY needs to come down. I think I'm getting close to be done. And point G, since you put it there, I'm going to put a weight going down. MG. So this is my free body diagram for this machine. Okay. Let's look at another one. Free body diagram following the structure. So this looks like a truss. Let's see if it is actually a truss. Do you see any forces that are applied anywhere but the pins or at the end? I don't see any. F2 is at B, P2 is at B, P1 is at F. So every member that we have is a two force member. So now we have to draw FBD of a joint or FBD of a section. Okay, if we want to analyze this truss, that's how we approach it. But for this problem, for the sake of this problem, I just like to draw it as like a rigid body, free body diagram. Meaning outline of it, and then put reactive forces AY, AX, and CY. This is a roller, this is a pin. Okay. Let's look at another one. Well, definitely not a truss. And it has moving parts for transferring and transmitting load, so it's a machine. It's a machine means disassemble. Disassemble. So let me see. I see 1, 2, 3, 4 members. Okay, so I'm going to draw 4 members. A top member, a jaw, doesn't have to be exact, lower member, and the member that connects these two together. Okay, outline of all of them. I usually like to start with the easiest one, which is a two force member. Okay, and I like to draw that one. Tension, compression really doesn't matter. Let's put it on tension. Sorry, compression. Okay, so that one is going to be FCD. FCD. Now that I've drawn this one in compression, then for the other members, I have to draw them opposite direction. Point. This is pin C, this is pin C, this is D. F, C, D. Look, one of these forces is compression, meaning it's moving towards the pin, towards the member. Every other force is compression too. Remember, FCD here is pushing on the pin. Here, it's pushing on pin D. So once one of them is compression, all of them are in compression, and they're all the same magnitude. Okay, let's look at the top member. I see a 5-pound force on it. Then I see a pin at point B. The first one, it really doesn't matter which way I draw it. BX, BY. They're unknown. I have the freedom of put them wherever I want. But on the second member, when I want to put forces on pin B, I have to draw them opposite of the first one. BX, BY. So now look, what happens if I put this point on this point? Basically put it back together. So BX and BX are going to cancel each other, and by are going to cancel each other. So that is important, that once you figure out the direction of one of the pins, when you want to draw the common one, make sure that it's opposite direction. Anything else on that jaw that I see? Yes, I see at point A, I see a smooth contact, so I see a normal force at point A. I see another pin, pin E. Let's do EX, EY. They're unknown, so I can draw them in any direction I want. But for the second pin E, I have to draw it opposite of the first one. There we go. And missing anything here? The only thing missing is a 5 pound here, and that's it. Oh, I think I'm missing another. This point A is contacting two of the members, one there, one here. Kind of right there. Okay, it looks kind of crazy, but we're gonna see how to simplify, how to be smart about it, how to pick the correct free body diagram that we want and solve it. So we had a 2-force member and bunch of multi-force members. All of the other ones are multi-force members. Let's look at another one. This also looks kind of like a truss, but if you look at this member AD, there is a distributed load on it. So if we take the area of this load, put it at the center of the area, we're going to have something like this, F1. Now you see the force is not only at the pin, and that makes this structure a frame. Once it's a frame, disassemble. I don't know if disassemble has 2s or 1, but anyway. 2-force member, 3-force member, because here, 2-force member, multi-force. It's not a 3-force anymore. Okay, so let's take it apart first. There's one there. There's one here. One member here. And one member here. Okay. This is CB. This is A, D. This is D, C. This is E, F. All right. Let's just start. I usually like to start with the 2-force members. EF. Doesn't matter if I draw it compression or tension. But as soon as I do that, I have to go to the other members that they have the same pin and put an opposite force on those two. So let's put an opposite force here. Okay. The next 2-force member I have is CD. So I like to put this one in tension, just because I put the other one in compression. Remember, as long as they're unknown, you don't know. It doesn't matter. I have to put an opposite force right here, force CD, and another opposite force right there, force CD. Remember, I told you wherever you see a pin, put a CX and CY, but I do not put a CY here. Why? Because I put a CY there, I don't have anything else here to cancel it, and that makes it an unbalanced force. And when I put them back together, there is some extra forces there. Okay, do I miss anything? Okay, yes. B is a pin, so I like to put a BY, and let's see. Yes, BX. Or no, that makes it wrong. I have to put BX this way, because this is a 3-force member. All of those forces, the resultants, needs to be concurrent, meet at one point. Okay. Here, on the other hand, AX, I don't know which way to put it because it's not a 3-force member, it's a multi-force member, and I have a F1 here. So this one, to be clear, a 2-force, a 2-force, a multi-force, a 3-force member. It's very important that you recognize those, and based on those put your forces, because look, being a 3-force member dictates that we put forces in this particular direction, otherwise it makes it wrong. Okay, the last example that I have for you is very similar to the other one that we had. Let's see, 1, 2, there are three members, or 1, 2, 3, 4 members. Okay, take it apart. Well, it's perfectly symmetrical, so I just draw two of them. I draw this one, which is AB, and then I draw the handle also, point E has a C, has an A. Okay, so let's look at AB. AB is not a 2-force member. I don't think there is any 2-force member or 3-force member. They're all multi-force. Why not? Because the forces are not only towards end of it. There is one contact surface here. Let's call it whatever, Q. Right there. Point B is a pin, so I like to put a BX and BY on it. Point A is a slot, so it's like this. It can move in this direction, but it cannot move in Y direction. So it only has a vertical force A. Okay, so that is my multi-force member. So now let's see. Point A has a vertical AY going up, so in this one it needs to have a vertical AY coming down. Point C, I can just put a CX and CY on it. Point E, I can just put an EX, and let's put this one pointing down on it. And there is a 50-pound force on it. You can draw the other two members as practice. They're going to be exactly symmetrical but opposite of the other two members that I drew. DE, and this one is D, C, and B. You guys do that as a practice.